Hello everyone, welcome to today's live interactive session on geology on soil volcanics. Today is our eighth week of discussion session, and slowly we're coming towards the end of the course. So, till previous session, we discussed about the many things, including consolidation and the shear strength. We solved a lot of problems from the shear strength topic. And in today's session, what we are going to do is that we are going to start the topic of retaining walls. Okay, retaining wall and earth structures. Those things we are going to start. We're just going to see the basics of those, and then uh, we are going to solve the problems as usual. So let us slowly proceed with today's class. So after today, we will be having three more sessions. So we'll be having the 11th and the 12th week session, and then we will be having a 13th discussion session the day after the 12th week session. All right. So yeah. So let us start the session for today. So earth pressure on retaining wall, we can have three cases. Okay, so what is earth pressure on retaining wall? Earth pressure is nothing but the pressure exerted by the backfill soil on the retaining wall. So retaining wall are what? Retaining walls are actually what? Structures that retain the soil behind it, right? Retaining walls are structures that retain the soil behind it. So when you have a soil behind a retaining wall, it obviously it's going to push on that, exert some pressure on the retaining wall. It's going to push on that retaining wall. Now, the earth pressures, the pressures that are exerted by those backfill soils on the retaining walls can be of three types. Okay, can be of three types. So one is our earth pressure at rest, then we can have active earth pressure, and then we may have the passive earth pressure. So earth pressure at rest means that retaining wall, the retaining wall is not moving in any way. Okay, the retaining wall has zero lateral strain. Okay, zero lateral strain. It's there in the place. It has zero lateral strain, and then you have the backfill soil. In that case, whatever pressure is exerted by the backfill soil on the retaining wall, that is my earth pressure at rest. Then we have the active earth pressure. Active earth pressure means the retaining wall actually moves away from the backfill. Okay, so you have the backfill here, retaining wall moves away from the backfill. In that case, whatever pressure is exerted on the wall is called the active earth pressure. And then we have the third case, or that is the passive earth pressure. This is when the retaining wall moves towards the backfill. Okay, the retaining wall moves towards the backfill. In that case, the earth pressure exerted by the backfill soil on the wall is nothing but our passive earth pressure. Okay. Okay. So hence we have three types of earth pressures. Earth pressure is rest, active earth pressure, and then we have the passive earth pressure. All right. So now let us see what active earth pressure. So as I said, active earth pressure is when the wall moves away from the backfill, right? The wall moves away from the backfill. This is the backfill, and we have the wall is moving away from the backfill. That is the earth pressure at active earth pressure. Okay, that is the case of active earth pressure. So generally, when the wall moves away from the backfill, we can have the failure wedge. So generally, actually what happens, we have a circular failure wedge that may, you have circular failure path that may develop. Okay, so this is the interface where you have the shear strength of the soil. It is acting in the opposite direction to the sliding of this soil wedge. Okay, so Rankine actually in Rankine's earth pressure theory, Rankine defined this failure surface is a planar failure surface. So planar failure surface means straight line. Okay, planar failure surface means straight line. So so what happens when the soil is when the wall is moving away from the backfill, this soil wedge, this failure soil wedge tries to slide down. Okay, to slide down, and then obviously to resist this sliding, we have the soil shear strength that is mobilized. Okay, shear resistance of the soil that is mobilized. And uh, one more thing you have to notice here, that the failure the failure line, okay, the boundary of the failure wedge makes an angle 45 plus 5 by 2 with the horizontal, where phi is the angle of internal friction. Okay, and also PA is nothing but our what? PA is nothing but our this active earth pressure that is resisting the earth pressure that is acting, and it makes an angle delta with the horizontal. Okay, because that if you consider some, when and only you consider some uh, roughness between the soil and the wall, there will be some friction angle delta between them. So that is what the PA is going to make with the horizontal. If and only if you consider in your analysis, you consider that there is going to be friction. The wall is a rough wall. Okay. Okay. And if you consider that the wall is a frictionless wall or a smooth wall, there is you won't have this delta. Okay. Right. Then you have the passive wall pressure. Passive wall pressure is when the so, the retaining wall moves towards the backfill. Okay, retaining wall moves towards the backfill. Okay, that is the case of the passive wall pressure. Okay, in the passive wall pressure. So obviously here the soil wedge, the failure wedge, it tends to move upwards. Okay, failure wedge tend to move upwards. So hence my resisting forces will develop downwards. Okay, and W is the weight of the failure wedge that is acting downwards, right? And here you see the angle made by the failure plane. Okay, the planar failure plane with the horizontal is 45 minus 5 by 2. Okay, 45 minus 5 by 2. Okay. Okay. Then you see a graph here. So here it shows that. So this is the at zero lateral. So this is the movement. Okay, or the lateral strain. Okay, that is shown in the x axis, and in the y axis you have the pressure that is on the thrust. So you can see that at zero movement, that is the at zero movement, that is the earth pressure at rest. The earth pressure at rest, you have the this P naught, that is the earth pressure at rest. Okay, earth pressure at rest. Okay, and then when the retaining wall moves away from the backfill, we mobilize the active earth pressure. So the active earth pressure is here. Okay, this. Okay, and when the retaining wall moves towards the backfill, you have the passive earth pressure that is here. Okay, so you can see a larger. So if delta P is the amount of distance, or amount of the strain that has to be in the retaining wall to mobilize the earth pressure forces. So you can see delta P is quite greater than delta I. So a larger amount of displacement is required to mobilize the passive forces than the active forces. Okay, the active earth pressure. Okay, then the passive earth pressure. A larger amount of displacement is required to mobilize the full passive earth pressure than the active earth pressure. Okay. Then also you can see that the value of the passive earth pressure, obviously, so in the center, in the middle, you have the at rest earth pressure. Higher than that, that will be the passive earth pressure, and lower than that will be the active earth pressure. Okay. And yeah. Oh, yeah. And you might be thinking that when do you actually have the passive condition? Okay. When does the this field, when does the retaining wall actually move towards the backfield? You might be wondering about it. So say you have a retaining wall like this. Okay. Sorry. To straight. Okay, so say you have a retaining wall. Okay. And you have a backfill soil here. Okay. And this is the ground level. Okay. This is the ground level. So there is a tendency for the retaining wall to move away from the backfill. So it will be something like this. So you can see obviously in this top portion, this side, you will have what? You will have the active forces that develop. But in here, this place, you will have the this side also you will have the active forces, and here also you will have a passive force, the toe region. Okay. Okay. So this is the condition. Okay, this is the condition. Just give me 1 minute. Yeah. So now let us see the more circle representation of the same. Okay, the pressures. So here at the center, this is the earth pressure at rest. That is the vertical, or not earth pressure at rest. It is the vertical. This point, that point represents the vertical force that is acting. Okay, that is the vertical force that is acting. Okay, it is the vertical force that is acting. Now this P naught point, this point presents the earth pressure at rest. So you can have a small more circle here, and you can see nowhere this more circle is touching the failure envelope. Okay, it's not touching the failure envelope at any point. Now, for the active case, if you want to get the active earth pressure, what you want to do? You want to draw a mode circle in that way that is tangent to the value envelope. Okay, this mode circle, and this point will give you the active earth pressure. Okay, so here this point represents the failure point. Okay, fix a tangent, right? So that is the failure point. And if you draw this angle, this is nothing but 45 plus 5 by 8. Okay, similarly, if we extend this in, extend the circle in this direction. Okay, this point will give you the passive earth pressure. Okay, and this angle here, 45. Okay, so how do you get? So first say you have this, right? So you have the vertical stress that is acting. Okay, the vertical stress that is acting. Now this vertical stress is nothing but my sigma 1 in case of my P naught and my active earth pressure. And what is my sigma 3? Sigma 3 is nothing but my P naught or and PA. Okay, and okay, okay, and in case of the passive pressure is as the passive pressure is higher, okay, higher, that time the sigma V is nothing but my sigma 3, and my passive pressure is nothing but my sigma 1. Okay, that is the major principles. Okay, and this is my minor principles. Just a second. Yeah, so active pressure at the earth pressure at rest is always less than my vertical pressure, right? It's always that, so the earth pressure coefficient, so the some coefficient times the vertical pressure gives me the earth pressure. Okay, so that coefficient is always less than 1. Okay, for passive pressure, for active pressure, and for your earth pressure at rest. And for passive pressure, that coefficient, or the earth pressure coefficient, which when multiplied with the vertical stress gives my earth pressure, that is always greater than 1. Okay, in case of by passive pressure. Yeah. So next we have let us see how to get the earth pressure at rest. Okay, so earth pressure at rest means there is no, as I said, there is no horizontal strain. Okay, there is no lateral strain or horizontal strain. And say you have sigma V that is acting, right? So you have a sigma particle stress that is acting onto the soil, and obviously my P naught, that is my earth pressure at rest, will be less than sigma V. Now my horizontal strain I can write as 1 by E, the horizontal stress, minus mu, that is the Poisson's ratio, times now Py plus sigma H. right? From the Hooke's law. Now, okay, from now next, as I said, my horizontal strain is 0. I can have sigma h mu sigma h equal to p naught is equal to what? Mu by 1 minus mu times sigma p. Now, what is this mu minus 1? Mu minus I can write hs p naught s k naught times sigma v. Now, this k naught is, it is the coefficient of earth pressure at rest. Okay. So mu by 1 minus mu is nothing but the Poisson's ratio. So generally, so is a Poisson's ratio of say 0.3, 0.35 maybe. Okay. So this will always be less than 1. So say mu is equal to 0.3. Then what is my k naught? What is my k naught? 0.3 by 0.7. So 0.3 by 7, 0.43. So you can see it's what is less than 1, right? So the earth pressure at rest will always be less than the vertical stress that is acting. Okay. Now next we can discuss the Rankine's earth pressure theory for cohesion losses. So Rankine gave a theory to determine the earth pressure for cohesionless soil. Okay, for cohesionless soil, later it was extended to cohesive soil. Okay, and then the theory was further extended by Coulomb to include the friction between the uh, wall, okay, the wall and the soil, okay, wall surface and the soil. So Rankine's earth pressure theory actually considers that the contact between the soil and the backfill soil and the uh, surface of the retaining wall is what frictionless. Okay, so it considers that the backfill the retaining wall surface is smooth. Okay, smooth, and there is no friction between the retaining wall surface and the backfill soil. Okay, then Rankine considered that. Okay, in his analysis. Later, Coulomb later extended Rankine's theory by considering the friction between the backfill and the retaining wall surface, and also he considered other factors like the inclination of the backfill soil and all those things. Okay, so as we discussed a while back, so this P1 is my at rest position, or at not at rest, the vertical pressure. So this is my vertical pressure. Okay, and this circle is the active circle, and this is my passive circle. Okay, and both of them have reached the failure. Okay, as both of the circles are touching the Moore Coulomb failure envelope. Okay, so both of the cases we reached a failure point, but the inclination of my failure point is different. Is different with the major what to say uh, with the major principal plane. Okay, it's different. Okay, for this one it's 45 plus 5 by 2. For this one it's 45 minus 5. So with the horizontal, sorry. Okay, the inclination with the horizon. Okay. Okay. Just a second, I was just saying something. To correct this. Let's say this is the returning wall. This is the backfill. So this would move like this. So you have the active soil wedge here and passive soil wedge. Active wedge, passive. Okay, these angles you know by now. 45 plus 2 and this is 40. Yeah, this is okay, passive resistance. A second, I will just check one thing. Just a second now. Seeing something. Just a second. Okay. I was just checking something with the book. I just wanted to show you this. So, in active and cassibis, there are a number of possible failure planes, right? So all these failure planes are inclined at the same angle. Okay, so you can have something like this. I should just turn off. Uh, yeah. So you can see here because all the failure planes are parallel to each other. So this is the case for the active case and this is for the passive case. So you can see we have two sets of failure planes. Okay, two sets of possible failure planes that are possible because here in the mode circle also you can see you can have two sets, right? So saying two sets. So here also you can have two sets like this. Okay, one at the top and at the bottom. So conjugate pairs. So similarly, so is in the actual if you want to draw it like this, so you can have two pairs. Okay, so here these are inclined at 45 plus pi by 2 and here these are inclined at 45 minus pi by 2. Okay, so this is what I wanted to show you. Okay. Okay. So in active case, the angle made is 45 plus pi by 2 with the horizontal. That is now horizontal is the major principal plane in case of active. Okay, in the case of active, the horizontal is my major principal plane, and in case of passive, it is 45 minus pi by 2 with the horizontal, and the horizontal is my minor principal plane in case of the passive case. Okay. Yeah. Yeah. So, mm, just verifying something regarding the Moore circle because yeah, all right. So now let us go back. Uh, Okay. Yeah. Now let's see how to get the earth pressure coefficients of active and passive case. So KAN, KP. So you remember from the previous session class about this particular relation, right? So you remember this is the basic equation. Okay, basic equation which we get from the Mohr circle. So C is 0. So we can neglect the other part. Now for active case, what is the vertical? You have sigma 1 will be my vertical stress, and what is sigma the horizontal stress? The horizontal stress of the passive earth pressure, active earth pressure is going to be my sigma 3, right? So now if you want to put it, you will have sigma V is equal to PA 10 square 45 plus 5 by 2. Okay, so from here I can get PA is equal to 1 by 10 square 45 plus 5 by 2. Sigma V, I can write PA is equal to K times sigma V. What is my K? K is 1 by 10 square 45 minus 5 plus 5 by 2, that is 45 minus 5 by 2, also equal to 1 minus sine phi by 1 plus sine phi. Similarly, for the passive case, what sigma 1 is which one? Sigma 1 is my passive earth pressure, and sigma 3 is my vertical. I can write P is equal to sigma V 10 square plus 5 by 2. I can have P is equal to Kp times sigma V. Kp is 10 square 45 plus 5 by 2, which is plus sine phi minus sine phi. Okay, so this is how you get coefficients Ka and Kp. Okay, now also one more thing, if you see Ka is 1 by Kp and vice versa. Okay, K or Ka by Kp is equal to 1. Okay, now these are various some of the cases that okay, these are some of the cases that we may discuss. Okay, various activities. So this is a dry submerged or so dry submerged and partially submerged. So first let us see the dry condition. So you have a dry backfill soil. In that case, you are going to have what? You're going to have this triangle which gives us the PA. So area of this triangle is going to give us the PA. Okay, so at any depth Z, what is the earth pressure? K into gamma into Z. So gamma into Z is what? My vertical pressure, and K times gamma vertical pressure will give me the active earth pressure. And then similarly, so at depth at H, at that for throughout the height of cell, so at depth H, we have K times gamma into H. And then if you take area of this triangle, you will get PA, that is the thrust value of the force. Okay, and similarly for the active passive case also. Okay, similarly for the passive case. So now if we have a submerged condition, okay, submerged condition, then first case is same. Okay, okay, this area of the triangle, but notice that we have to use the submerged unit bit only and not the saturated unit bit. Okay, you always use the submerged unit bit. So K times gamma prime times H. Okay, they will give me this. Then the area of this is going to give me PA, plus there will be some lateral thrust that is coming from the water, because all of the backfill soil is submerged, right? So there will be some lateral thrust from the water, that is obviously from Pascal's law, right? So water exerts equal pressure in all directions, and you are also going to exert equal pressure in the lateral direction also. So similarly, we're going to have another triangle, okay, that is gamma W into it. So area will give you the PW. Okay, so that that's it. Yeah, I'm writing for this one. Huh? P is equal to A times gamma into Z small p. So PA is the area half into K gamma Z into the height. Okay, so this is what I need to have Z. Now if I write for the total, so this is, if I want to find out the area, this will be its field area half K gamma H square. Okay, similarly for PP also I can get half KP gamma H square. Okay, this case. Yeah. And for this case, along with this, you have to add this area also to get the uh, total thrust. To get the total thrust. Okay. Now this is for the partially submerged case. Okay, partially submerged case, plus over that you have a what to say, you have some surcharge. Okay, you have some surcharge Q that is acting. Now due to the surcharge Q, you can have this triangular rectangular pressure distribution, right? So thrust is same everywhere. So K times Q, K times the vertical thrust Q will give you the this rectangle. Okay, then area is going to give you PQ. Then comes the active thrust condition. Okay, active thrust condition. So this is my thrust from the thrust due to the Q. Okay, there is the surcharge. Now the thrust from the soil weight. So up to this side, first you write, you get this value K into gamma into H1, right? So this length is K into gamma into H1. All right. Now here the soil is submerged, so my gamma is going to change. So the gamma is going to change. So if the gamma is going to change, it's going to be K times what is the pressure at this level? This is the pressure at this level, gamma into H1 plus gamma prime into H2. So that is my pressure. So that times K will give me this length, right? This. So, so area of this whole thing is going to give me PA. Then also, as it is submerged, for the below part, I will be having some water thrust also. That also I need to consider. Okay. Now for cohesive soil. Now cohesive soil, what is the case? So you can have this thing, right? We have this case. So from here, can write. So if I write this term as N5, okay, twice secondary root over N5. Okay, I'm replacing this term. I'm writing, just writing this term as N5. N5 is equal to nothing but 10 square whatever plus 5/2. Okay, it gives you active. Okay, sigma V is sigma 1, PA. gamma z by as 2 by c root over n pi. This is my PA in case of cohesive soil. Okay. So you can see how the arrangement looks. The arrangement looks something like this. So initially at when the z is 0, you have minus twice c by root over n pi is the thrust. So then you have a point where you have the thrust as 0 and then the thrust becomes positive. Okay. So sometimes the question must be asked to find the depth at which the thrust is 0. So this is the depth. Okay. HC is also the known as the depth of tension cracks. Okay. Not HC by 2. Z naught. Z naught is nothing but the depth of tension. So you have the tensile forces acting in the upper part, right? So due to that, what happens? Generally, some cracks develop. If tensile cracks develop, then what is going to happen? If tensile cracks develops, then the soil is going to separate out from the retaining wall at that point. So there will be no pressure acting on the retaining wall at that point. So in that case, the area of this whole bottom part will give you the active thrust. Okay, area of this bottom part is going to give the active thrust. But if you have your, it is given in the question that there is no separation. Okay, there is no separation of the cracks do not develop. Okay, it's given in the section a question that the tensile cracks not develop. Oh, okay. If the condition is that tensile cracks do not develop, then there will be some tensile forces that is acting on the wall in the upper portion too. Okay, because it is specified that there is no separation between the soil and the wall. So in that case, this and this will get cancelled out, and the area of this trapezium will be give you nothing but the active earth pressure. Okay. Okay. So this is I have given when tensile cracks develop. Okay, that means in that case, when cracks develop, this will be my this area will give my PA, active thrust. And when do not develop, only this area will give. Okay, so this is tensile cracks develop, and this is tensile cracks not develop. Okay. And similarly, we can have right for the our passive case also. From here, finally, we'll get the passive pressure as okay. So here the difference is that here you get a minus sign in between. Okay, right. So here, but here we have a plus sign. So 2ic plus n pi root over n pi will behave as a surcharge. Okay, will behave as a surcharge. So hence it comes like that. Okay, it will be like a surcharge. A pseudo surcharge, you can see. Okay. Okay, next we have the case of inclined backfill. If the backfill is inclined, then you can have these relations, inclined angle beta, then you can have these relations. Okay, that's all. That's the basic. Now just let us start solving some basic easy problems. Okay, just give me a second. Just have some water. Okay, so I hope everything is clear to you. Okay, so if you have any doubts, you can ask me. All right, I hope the things are clear. Yes, so a 15-meter high retaining wall. What's it? Okay. So 15-meter high retaining wall with smooth vertical back retains a mass of moist cohesionless soil with horizontal surface and the following properties. Compute the total lateral earth pressure at rest and its location. If subsequently the water table rises to the ground surface, determine the increase in earth pressure at rest. Okay, take a naught is equal to 0.45. So you need to calculate the earth pressure at rest. So it's just very easy. Wall that is here, that is 15 meters. Okay, we left P naught. So you get rectangle. It will be acting here, and this is at gamma into H into K naught. So if we want to find P naught is nothing but half gamma H K naught times H. This is first for the dry condition. Okay, so backfill is dry or moist, not submerged. Okay, this is what that condition. In that case, you do not have the water table here. Later, the water table rises to the top. In that case, we are going to calculate next. So this is going to be Newton per meter. And where is it going to act? It is going to act at 515 by 3. That is 5 meter from the bottom. That is the centroid, right? Now, next case is that if we have a submerged soil, then you have two triangles. So this is one. This is k naught gamma prime into h plus here one more. It is gamma w into h. Yes, w. The total thrust is P1 plus PW. Okay, let PP is better. Or not PP, it's P naught, right? Sorry, it's P naught. Not K, there won't be any K here. Huh? at 1438.36 meter. Okay, this gamma times to so how much is the increase in earth pressure? 628. So you can see due to the so due to water, a huge amount of lateral earth pressure increases. Okay, so you have to avoid the case of water retention in the backfill soil. You have to provide proper drainage so that whenever it rains or whenever it floods, so the water easily drains out from the backfill soil. If not, it's going to exert a lot of earth pressure onto the wall, which will lead to the the wall failure if not considered in the design. So you have to consider this. Okay. Okay. So let us go to the next problem. Okay, so just see this problem. A retaining wall 10-meter high retains a cohesionless soil with an angle of internal friction 35 degrees. The surface is level with the top of the wall. The unit weight of the top 3 meter of the fill is 1.6 tons per meter cube, and that of the rest is 2 tons per meter cube. Find the magnitude and point of application of resultant active thrust. Okay. So is my KA. Okay. Now at the top portion, yeah, so you have two layered soil now, right? So the top portion we are having something like this till here. And so what how much is this? This is 0.271 times 16 times 3. Okay. And if I want to write for the bottom, and so this one will be how much? 0.271 times 16 into 3 plus 7 into 20. So this is 16 into 3 times 2.271. This is the sorry, this is the other part. Okay. So what I can do, For this triangle, this one is 0.271 times 20 into 7. Okay, so I can divide this into three parts. So 1, 2, 3. So two triangles and one rectangle. Okay, so I can find the what to say. You can find your PA as half into this one plus 7 7 square. So we are going to have wait a second. 19.5 plus 1 going to be 243.3 per meter. Okay, all the areas added up. That's all. Okay, now if you want to find out the point of application of the resultant, okay, point of application of the resultant means the centroid of this particular figure you have to find out. Okay, that's all. How to do that? 19.5 times how much? 7 plus 3 by 3, that is 8, plus 91 times 7 by 2, that is 3.5, plus 132 times 7 by 3. Now what is 3.22 meters? So that means if this is my wall, which is 10 meters, then the resultant active thrust is acting somewhat here. The height of y is equal to 3.22 meters. Okay. Next problem, retaining wall 5 meter high, retain equationless soil with an angle of internal friction 35 degrees. The surface is level with the top of the wall. The water table is below the bottom of the wall. Determine the percentage change in the activity of the water table as the ground. Okay, similar. Okay, so here the retaining wall, which is 5 meter high. Right. This is when dry condition. So let me do this. X square is going to come out as 57. Now, if the water table rises to the ground, then you are going to have two triangles. Directed thrust. Percentage increases. You can see a lot of increase in the lateral thrust due to the water. So, okay, due to water, lot of increase is there. Next, a retaining wall 10-meter high retains a positionless soil with an angle of internal friction 35 degrees. The surface is level with the top of the wall and the water table is below the bottom of the wall. There is a uniformly distributed surcharge of 63, intensity of the backfill, the unit weight is given, and the active earth pressure per meter length and its point of application. Okay. The wall is 10 meter, you will have some PA that is acting at a meter 5. So due to the surcharge, A times Q this is going to be Ka times 10 meters into my gamma. So my gamma is 20. Ka is similar to the previous problem, 35 degrees, so 0.271. So my total is going to be times Q, it is 63 times the height, it is 10 plus 0.271 times 20 times h square 170.73 plus 271 is going to be 441.73 cubic meter. So y is okay. I hope this is clear, right? The next retaining wall, 6-meter high, retains a cohesionless soil with an angle of internal friction 35 degrees. G is 2.69 and is the porosity 40.5%. The surface is level with the top of the wall and the water table is 2.5 meter from the top of the wall. We determine the active pressure per meter length of the wall. Okay. So a wall like this, which is 6 meters Provisionless. This is the backfill, top of the backfill. Water table is somewhat here, and 5 meter. Okay, the soil is dry here, and it is submerged here, obviously. Okay. So my porosity is given. From there I can get the E, that is the void ratio. That's 681. Now I can get my dry unit weight. So submerged. Okay. Now for the top, it's dry. It will be what? Ka. Gamma D times 2.5. Okay. Now at the bottom, yeah, bottom you're going to want something like this. This is, see, Ka gamma D 2.5 equal to 2. Then you have this triangle, which is nothing but K submerged 3.5, and then finally you have the water pressure, nothing but gamma W times 3.5. Okay, this is my 4. So P1 3. Finally P4, which is my Y, that is the centroid is Okay, so I forgot to write the total sum up. So PA is is 1.68 meters. So the wall, the water. Okay, the PA is acting somewhat here. Diameter. It. Yes. Even it. Same, we have to find the condition is given to us. We need to find out the active thrust. Okay. So A1 is and KA2, you already know it's 0.271, 35 degrees. Submerged is 19. Okay, so now you 3 meter like this. For the part stop, you can have this. Okay, now for the second, here, what is the pressure? The pressure is 3 into 16, but my Ka2 has changed. Ka has changed, so Ka2. Then you have the earth pressure times r gamma W 3. Okay, so now I can find out P1 to P4. Square P4. Sum all it up, sum all of them up. Now one last thing is the point of application. Okay, the wall to find out the point of application. A I, so what is Y? meter. Okay, let's see this. The soil mass is retained by a smooth inclined wall of 6 meter height. The soil has a bulk unit weight of 20 kilonewton per meter cube and an angle of lateral friction 16 degrees. The top of the soil is level with the top of the wall and is horizontal. If the soil surface carries a uniformly distributed load of 4.5 kN per meter square, determine the total active thrust on the wall, perimeter of the wall, and point of application. So, this is actually given in the question, the diagram actually. Okay, so this is actually given to you. Mm, yeah, so I like the wall is like this, right? So if this is B, this is A, this is C. Okay, so this is 18 degrees and this is 6 meters. Okay, so this AC length I can get as 6 times 10, 18 degrees. Why? So what we are going to do this part, we are going to uh, but this weight of the soil we are going to take. Okay, later this the weight that is there in the ABC triangle. Okay, the weight of the soil we are going to take. Then you have so your first you have this. So this is 4.5 times Ka, and then you have hmm, how much? Okay, times 20 times 6. And what is my Ka? Sine 16 by is 0.568. Okay, so one as usual. Now, where is this PA acting? So you have something like this now, right? So this is the wall. Okay, and here you have your this soil, and this is what where your PA dash is acting. That is why. Now I want to find the this PA. PA is nothing but the resultant of this PA dash and the weight of this soil wedge. Okay, so weight is half into 6 into 6, 10, 18 degrees times 20 times 116.97 per meter. Therefore, so now, and so we have this PA dash and W, so we'll have resultant PA angle alpha. So PA is come out as 249. Okay, the wall, yeah, PA equivalent alpha. Fine. Let's see this. Yeah. An unsupported excavation is to be made in a clay layer. The soil has a bulk unit weight of 18 and an internal friction of 16 and CO30. Calculate the depth of tension cracks, maximum possible unsupported depth. Maximum possible unsupported depth means 2y z naught, that is h depth. Okay. Draw the active pressure distribution diagram. Okay. So my PA is what? So here, in case of C5 soils, you have If you remember, we have this kind of diagram, right? So the if this depth is z naught, the maximum supported depth is twice z naught to h naught c. Alright, so hz naught is nothing but, this is 0, PA is 0, so from here I can get 2ic gamma root over AA. That is my z naught. Now 2ic gamma over K. Ka you just calculated for 16 degrees in the previous problem, right? 0.568. So what's the, how much is it's not 16 degrees, it's 10 degree. Okay, over K. So K is so from here you can get 2 into 30 gamma. Therefore, gamma is nothing but 18. It's 18. So from here you can get meter. So this depth. So this is nothing but the depth of tension crack. So maximum possible unsupported depth is twice z naught is 2 into 3.973 795 meters. Okay, and you want to draw the pressure diagram too, so the pressure diagram will be nothing but so yeah, so the pressure diagram and to draw it will be something like this. This is the 2iz naught, which is 7.95 meters. Okay, this is minus plus, so this is minus 2ic root over n phi. This is plus 2ic root over n pi. This 2 into 30 by 10 45 plus 50.34. Okay. Okay, next problem. A smooth vertical wall 4 meter retains a cohesive soil backfill with a bulk unit weight of 18 kg per meter cube and an angular weight of deflection 0 degrees and C is equal to 10 kPa. Calculate the depth at which active earth pressure is 0, depth of tension crack, depth at which total active thrust is 0, total active thrust per unit length of the wall when tension could not develop, and draw the active pressure distribution center. Okay. So we have a 4 meter high wall. So there we are going to have some, obviously we're going to have some arrangement like this. Okay, so this is going to be negative, this is positive, so this will be I z naught. Also it's positive, it's twice z naught, or twice z naught is equal to h naught, right? Now how much is z naught? Z naught is 2ic gamma root over Ka. So for 0 degrees, sin K is what? K is 1, right? So for phi is equal to 0 degrees, my K is 1. So I can get 1.11 meter here. If I put all the values, so hence this one will be how much? 4 minus 2 into 1.11. So it's going to be 1.78 meters here. Okay. So first is depth as we are, earth pressure is 0. Pressure is 0 is 1.11 meter from top. Obviously it's depth, so from top to only. Now depth of tension crack is also Z naught, so 1.11 meter. Then depth at which total active thrust is 0. Total active thrust is 0. Means total 0 means depth. Yeah, so that is H naught twice Z meter. Okay, so till this depth H naught total active thrust is 0 because negative and positive will cancel each other. Hence, the total active thrust becomes 0. Total active thrust now I have to develop the total active thrust per unit length of the wall when tension cracks do not develop. So when tension cracks do not develop, this is going to cancel. So just this area is going to give me my what? This area is going to give me my active earth pressure, right? Active earth pressure. So what is this length? This length is Ka gamma H minus 2Ic over Ka. So it's nothing but if we put all the values, you will get 52 kilometer square. So my Pa is half into 52. When tension cracks do not develop. Yeah. So the area of this trapezium, right? So half sum of parallels is 52, and this is how much? This is 20. Okay, that is 20. This is also 20. So this is also 20. Okay. 52 plus 20 times 1.78. So this is 64.08 per meter. I have to find out the point of application. The point of application of PA will be somewhere here. The distance of Y. So now let us find out. Let us calculate Y. Right, this is from the formula for the centroid of trapezium. 0.758 meters. Okay, this is my Y. Fine. Now let us solve the last problem for today. A smooth vertical wall 5 meter retains a cohesive soil backfill with a bulk unit weight of 18 kg per meter cube and an angular iteration 20 degrees and C is equal to 30 kp. Calculate depth of tension crack, total active thrust per unit length of the wall when tension cracks develop fully. Yeah, the backfill soil is given as horizon. Okay, so I hope everything is clear, right? It's clear, right? So if you have any doubt, you can ask me anytime. Okay, I hope it's clear. Okay, so you have a 5 meter high wall. So So what is my Ka? 0.9. Now, what is my Z naught here? My Z naught is 2IC gamma root over Ka to 230 to 0.9 will come out as 4.76 meters. So yeah, almost all of the 5 meter. That's a little bit just it's remaining. So I want to draw. It will be something like this. So this is the negative part. So this is negative part. This is my Z naught. And what is this? This is K times H1 minus 2 root over Ka. So 0.49 into 18 into 5 minus 2 into 30 root over 0.49 is big 2.1 kilonewton per meter square. Yeah. So when tension cracks develop fully, so when tension cracks develop, only this area will come, right? So my A is half into 2.1 times 5 minus 4.76 half yeah 0.76, so it will be coming as 0.252 kilonewton per meter. Okay, so yeah, if you want to find out the y is nothing but 5 minus 4.76 by 3, that is 0.08 meter. So something here, but here, okay, here is acting, this is my y. All right. So with this, we will end today's session and hope that the problems were clear. The problems were quite straightforward and easy, right? Quite simple, straightforward. I don't think there should be any problem. Uh, uh, yeah, should not have any problem with this. All those stuff, okay? Because the problems are quite easy. Directly, we just use the earth pressure theories and the relations to determine all the values of earth pressure. Okay. So thank you so much for attending the session. And the next session, as usual, will be on the next Monday, coming Monday, that is on the 7th of April. 7th of April from 6 to 8, 6 p.m. to 8 p.m. to discuss some more problems. Okay. So thank you so much for attending. If you have any doubt, please feel free to contact me anytime. Yeah, and I will be more than happy to help you out. So thank you so much. Thank you for attending the session. Have a great evening. Thank you. Okay. Thank you.